Good morning, Calc 2 students. Dr. Shragi here. And as we continue plowing our way through Chapter 3, if you're thinking, man, this guy who invented the calculus is not my friend, apparently, you're not entirely wrong. Thanks for nothing, good old Isaac over there. He is definitely kind of a mixed blessing. I mean, obviously, it's an amazing thing. The guy invented calculus while sitting around in his parents' house during a pandemic. He did an amazing thing. But if you're starting to think, man, I am a little bit lost in this class, I do not even remember what these integrals are for. See, like all we've had is just large amounts of trouble of trying to figure out what kinds of methods we can use. And it's been a long time since we've had a proper story problem as to what to do. And all I want to know is there's got to be a better way to come up with these guys. Well, you're not the first and you're not the last calc student who's going to feel that way. So I'm wondering if we could come up with today maybe some simple examples of that are simple might be a strong word, but simpler than what we've been learning, ways to come up with integrals in the sense of an area under a curve. It does feel like we could write to Isaac Newton and get him back in the 1660s to maybe come up with some slightly better ideas. See, here's the deal. Like, here's an example that at first blush, well, I mean, we've seen worse. It doesn't look like this would be the end of the world. But this is actually an extremely difficult integral. I can pop this thing into Desmos, and in fact, Desmos knows some tricks and actually even comes up with the correct answer right there. But if I was just trying to find the definite integral from 0 to 1, so along the x-axis from 0 to 1, I'm just trying to find the area under the curve. Well, I'd invite you to think about things like integration by parts or trig substitution or any of the other awful methods we've learned, and there'll be more. It doesn't immediately come obvious how any of those would have helped on this. And in fact, this is a pretty tricky integral. Well, you might think these things we learned about before about things like midpoint rule or trapezoid rule would be helpful here. But see, like in this case, the graph is so badly behaved. If we tried to come up with like little trapezoids or little, what's the right word? Little rectangles to try to represent it, it would actually not get closer anytime quickly to the real answer. We'd have to go into millions and millions of trapezoids before we'd even start getting into something we'd feel comfortable with for an answer here. So rather than do either of those methods, both of those methods also kind of fail here. Not so much fail, they just would have to work really hard to get them. Let's try something else, something new, something easy. And because it's kind of hard to illustrate it with, let me go back here for a second, because it's kind of hard to illustrate with this crazy integral that's bouncing around up and down to show you what this one is doing, let me instead show you on this much simpler integral, 2x squared. The integral of 2x squared from 0 to 1 is something we can do in this class. We've done this before. We know how to assess this. It's just a polynomial. For what it's worth, it's 2/3, as you can see on there. But let's say we didn't know that, or perhaps more accurately, some algorithm we were writing on a computer program. It had no way of knowing that. What would be another way we could come up with this integral, this area under the curve? Well, another possibility that I don't think Newton ever thought of is we could think about that area under the curve as being the fraction of a larger area, in this case what I have in that red box. That red box has to bound the area that we're integrating. It has to completely enclose the area that we're trying to integrate. I am trying to just get the area under the curve that's inside of that box. That box goes from 0 to 1 on the x-axis and as high as it needs to go on the y-axis. In this case, it goes up to 2. Okay, so this is our little area that we're trying to integrate. And we're thinking of it as just a piece of a rectangle. The rectangle itself is just has an area of 2 in this case. Now, I'm going to picture we're trying to do this before computers could help us. One thing we could do is throw a dart at this graph, and it would just hit some spot randomly on the graph. This could literally be something like a dart, although in our modern times, this is going to be just a random number. We're going to pick a random number between, in this case, 0 and 1 for the x-axis, and a random number between 0 and 2 on the y-axis, but that will just be the coordinates of this random point. Now, that random point may fall above or below the curve. And that's actually a really simple thing to compute, because basically we just find the value of f of x at that x, and if our value is greater than that, we're above the curve. If our value is below that, we're below the curve. It's a matter of one line of computer code to decide if you're above or below this curve. All right. What if I didn't throw just one dart? Boop, boop, boop. I threw lots of darts. Some of these guys will be above the curve, and some of these guys are going to be below the curve. And there's a total number n darts that we have thrown. So if I'm keeping track here, I could talk about another fraction, the number of darts under the curve divided by the total number of darts that landed in that box. That would also be a fraction, and as it happens, that is an estimate of that previous fraction, the area under the curve to the total area in the box. You could pause the video if you want to think about that for a little bit and realize why that would have to be. They're not going to be a perfect match because, throwing darts has some chances. In theory, you could have thrown the darts and all of them ended up below the curve. But as a rough approximation, this will be probably pretty good. So the total area the area under the curve divided by the total area of the box will be approximated by how many darts landed under the curve divided by how many total darts you threw. Well, with a little algebra, you can pull total area of the box over off to the left-hand side, and now we have a way of estimating the area under the curve. Now, we got to just make a little computer program that effectively throws darts by picking random coordinates in x and random coordinates in y, and do this work here. Now, in this particular case, I know the correct answer is going to be 2/3, or 0.66667. I put together a little program right here. This is a little C program. There's not much to it here. Most of these lines are actually just setting things up. It's just a little computer program. Somebody who's had a computer class or something like that would recognize there's a little loop here where for n times, in this case, we're going to throw n is 100 darts. We're going to pick a random x and a random y, and I'm just going to see is the y below the f? Is it below the f of x curve? And then we'll come up with our estimate of the integral. So here we have, I'm running it with 100 darts. If I throw 100 darts, and I ran the program 10 times just to see how the answers varied, so I got 0.72, 0.78, 0.82, 0.6. These estimates are, well, they're in the ballpark of 0.6667, which we know is the right answer, but some are below and some are above. These are estimates. They're not perfect. But you know what we can do? Computers are fast. Let's throw another dart. Let's throw 1,000 darts. So I ran the program 10 times again, each time running 1,000 darts. Well, now look at these answers here. They all start with 0.6, except for that one. And actually, that's, for 0.667, that's not bad. Some of these guys are actually fairly close. Depending on, I say fairly close. I don't have a preconceived idea as how close I need to get these guys to the right answer. But if all I really needed to do was estimate the integral, this was not bad. How about if I computers are fast, how about if I throw 1,000,000 darts? When I ran this program, it computed 1,000,000 darts 10 times, like before my finger was even off the enter key. This is fast. And notice all of them now, all 10 times, it got 0.66. In fact, all of them are close to 0.666. We're getting to be a pretty good estimate here of what the true value of the integral is, just by throwing 1,000 well-thrown random darts. Now, there's lots of hang-ups there. The random numbers have to be truly uniformly distributed and all this kind of stuff. But there's a lot of technical details to getting this to work and that you can trust it. But you can see, it was just a few lines of C code that the truth of the matter is ChatGPT or Gemini or something wrote for me because I was feeling lazy and wanted to get it done fast. And I got pretty darn good estimates of this integral. Now, this particular one that was just the integral of 2x squared, obviously we could have done that on a scratch piece of paper in a minute or so. But we could also have done it this way. And for a much worse integral, which is nowhere near fun, and we know the correct answer according to Desmos is 1.504. Let's run that thing a million times. I just ran the program a million times. Actually, I ran it 10 times, each with a million points. And you can see all of these numbers are pretty close. I mean, I've got a pretty good estimate of this integral without doing any work. I just threw a million darts at it, each time deciding whether or not it was above the curve and keeping track of the fraction of how many were above the curve, below the curve, divided by how many darts I threw. After a million darts, the estimates are not bad. This is a technique called Monte Carlo integration. Monte Carlo here is in the sense as in like the gambling city in Southern Europe, someplace, France or something like that. I'm not sure where. It's kind of the Vegas of Europe, and it gets that name purely because we've invented a game of chance here. We effectively created a game, this darts game, that actually can solve a real mathematical problem, or at least maybe estimate a real mathematical problem. This is pretty clever. And in fact, this is used tons of times at any kind of time that, like, you can afford to spend a million computer cycles or whatever computing, estimating, but throwing a million darts, which often is the case. Often you can run these things, and this often works. Now, there are some limitations here, like you have to be able to bound the area you're integrating with a rectangle, and there's issues as to how many darts you'd have to throw, depending on what your estimate is of the ratio from the area under the curve to the area inside the rectangle. I mean, there's a lot of technical things. This, in fact, is a whole college course that I took, is this Monte Carlo integration. But honestly, it's a pretty slick technique. I mean, if you just have a little piece of code set up to do this and you don't need the exact answer, you just need an estimate, this is pretty clever. Are you going to be writing a Monte Carlo program? You are not. Rather, I want you just to understand the strategy behind it and know what its advantages and disadvantages are. And its advantages are that it can actually handle really complicated integrals. The truth of the matter is some integrals aren't even possible to solve using the methods in calculus, and some are possible but involve lots of complicated math. I mean, more like a graduate student in, pursuing his PhD in math would learn how to solve these things. Whereas, honestly, the Monte Carlo method works just fine. And it is relatively simple to implement. You saw I let ChatGPT or Gemini or something write a handful of lines of code, and it got done in, before my finger was even off the enter key. These are pretty straightforward, easy things to write. Now, it does have some disadvantages. You might have noticed that our estimates for the integral were kind of garbage when we only threw 100 darts, picked 100 random numbers. But they got a lot better when we did 1,000 darts. But the truth of the matter is a million darts wasn't actually all that much better, maybe another 1% better or something of an estimate than the 1,000 darts was. The truth of the matter is if we had needed an even better estimate and we had to go even farther, a billion darts or a trillion darts is certainly not out of the question. And then you're starting to talk some serious computer time. The particular slide here I put on here that it converges at a rate proportional to 1 over the square root of n. You don't need to know that. That was more just there to remind me. But the point is, if you're going to need high accuracy, this might not be the technique. Well, it depends on how much computer time you got to kill. If you're doing this calculation and that's the only thing you're doing before the screensaver kicks in, who cares? If you're doing this calculation and you need to do this calculation at every grid point in a numerical model of the atmosphere, and you need to do this at millions of points, thousands of times a second or something like that. No, this is going to be too wasteful. You're not going to be able to do it. And in fairness, it is just an estimate. I wrote on here that it's random error. It is a statistical estimate, and so there is some degree of random error. You saw how I ran the program 10 times at each size, and all the answers were slightly different. But you kind of get some sense as to what the overall integral would be. It's just an estimate. Now, the truth is, Isaac Newton would probably not have approved of this method. I mean, obviously, this is very wasteful. Nothing he could have done in the 1660s would have been able to reproduce this. He would have been like, so what? I'm going to just sort of have some student who's working for me throw the darts at a graph. Honestly, he wasn't even all that solid on graphs. The idea of graphs wasn't really a thing back in the 1660s. He certainly wouldn't have liked the gambling aspect of it. He didn't tend to like to leave things up to chance in general. You might remember he's extremely religious. He might have seen this as somehow gambling or something. He would not have approved. So let's come up with yet another method that would also be a way of estimating an area under a curve. And let's do this specifically for an application near and dear to my heart as a meteorologist. So what I want to talk about is thunderstorms. I don't know what you know about thunderstorms, but a thunderstorm is an updraft. Air is rising in a thunderstorm. At each height along the way, inside the thunderstorm, the air is rising. And the reason why the air is rising is that it is warmer than the air on the outside of the thunderstorm. Air rises when it's warmer than the air around it. It's more buoyant and it tends to rise. So like in this picture right here, the area around this developing thunderstorm the air around it is colder. The air inside the thunderstorm is warmer, so it experiences an upward acceleration. Obviously, this is something a meteorologist is extremely interested in being able to predict and know how strong that updraft is going to be, because that's a way of saying how strong the thunderstorm is going to be. To that end, meteorologists take measurements. Let me move my little window over here. Every day at about 100 locations around the United States, we launch weather balloons that have instruments on them. They fly up from the surface of the earth to a height of, maybe 15, 20 kilometers above the ground, and then they pop and they fall back to the ground. Whole journey takes about an hour. And we make graphs that look like this based on what the balloon observed and radioed back to the weather station as it flew. Now, this diagram has got a lot of things going on it. I just want to focus on a couple of things about it, though, that are about how we're going to figure out the strength of a thunderstorm updraft using an integral that Newton probably would have actually kind of approved of. All right. On this diagram here, the x-axis is temperature. And I'm lying to you a little bit. Wait a minute. I'm sorry. I have a mistake on the slide there. The x-axis is temperature. Forget that word pressure on there. The x-axis is temperature. The y-axis on this diagram is height. Well, okay, you can see actually on the diagram there, I don't know if you can see my mouse, but there's like 15 kilometers, 12 kilometers, 9 kilometers. The actual x-axis, the y-axis itself has to do with pressure. Pressure measured in millibars is on the surface, but we can focus on those little ticks on the side there that show height. That's fine. Now, there's different pieces of information being plotted on here, but I want to just focus on two of the curves that are plotted. One is the solid red line. The solid red line is the temperature that the weather balloon measured at different heights above the ground. So as it was flying upward, it was experiencing colder and colder weather, and then it hit a layer where it got warmer, and then it rose for a while, getting colder as it rose. Then it hit another little layer where it got warmer for a while, and then it got colder and colder and colder until it hit the tropopause, a layer of the atmosphere about 12 kilometers up. And from there on up, it was actually getting warmer as it went up. Whatever. The balloon saw all that. That is the air that if a thunderstorm forms, its updraft is moving through. This is the air around the thunderstorm's updraft. The other thing that's on here is that dotted line that's kind of brown. And that brown dotted line is going to be showing the temperature of the updraft when it gets to that height. So at first the updraft will be at this temperature, and then as it rises, it'll be at these temperatures. As it goes up, as it crosses each of these altitudes, we know what its temperature is. Okay, so in other words, if I, hold on just a second, there we go. Take a look at this. And let's just say, let's focus on that height I have highlighted there in blue. At that height, there's that blue line right there. My air temperature, which is that red curve, is to the left of the temperature of the updraft, which is that brown dotted line. At that height, the temperature of the updraft is greater than the temperature of the air around it. So the updraft is warmer than the air around it. It is buoyant. It's going to accelerate upward. It's not just going to rise upward. It's going to accelerate upward. Newton would have liked that part about it. He was all about forces and acceleration and buoyancy and stuff like that. He would have actually been kind of on board with this idea here, that we're finding a way of figuring out how buoyant the air is going to be at each height. So in other words, any place on this graph where the dotted curve is to the right of the red curve, That represents a level in the atmosphere where the updraft is experiencing positive buoyancy. It's getting stronger. There's a force pushing it to rise even more than it's rising now because the air is warmer than the air around it at that level. It's becoming more and more buoyant. In places where the separation between the red curve and the dotted line is far, that air is much warmer. The air in the updraft is much warmer than the air around it. It's experiencing a lot of buoyancy. Whereas a place where they're close, like down here around 3 kilometers, the air in the updraft is warmer than the air around it. Excuse me. But not a lot. It's not experiencing very much acceleration upward. It's already moving up. I mean, that's why it's an updraft, but it's not experiencing much acceleration to make it go faster than it was before. So this area between these two curves, between the red curve on the left and the dotted curve on the right, is about how strong the updraft is going to be. In fact, it's related to the kinetic energy of the updraft. Not related, it's actually proportional to the kinetic energy of the updraft. We need the area between these two curves, because the area between those two curves, bounded at the top and the bottom by where the red curve and the dotted curve crossed, is a way of saying kinetic energy of the updraft. How strong is your updraft? Which is going to be very related to like production of hail, production of lightning, etc. A very practical reason we would need this. All right. Area between two curves. Now that sounds like something we've talked about before. Area between two curves, that sounds like an integral, right? Now, actually, it's the difference between two integrals. When we have the area between curves, it's the integral of whichever one is supposed to be, the bigger one minus the integral of what's going to be the smaller one. So in this case, it's actually the difference between the integral of the dotted curve minus the integral of the red curve. There's a handful of technical details in here, like we would actually have to turn the graph 90 degrees for this to work if we were going to be doing it. But here's the deal. We're not going to do it. Because both of the integrals, the integral of the red curve and the integral of the dotted curve, are ludicrously difficult. They are not something even PhD meteorologists do, okay? They are not a pretty calculation. Now, these days, in the era where there are computers, the truth of the matter is a computer is going to handle this. A computer is going to take this integral using something like, it could be Monte Carlo techniques, although I think most of the time it's more of a trapezoid rule thing. But because a trapezoid rule will give an estimate of the integral of the dotted curve, a trapezoid rule will give an estimate of the red curve, and then we'll just take the difference between them, and it'll work just fine. But that would be a lot of work to do before there were computers. And this quantity, that area between the two curves that was highlighted back here, that area there, that area is called CAPE. It's an acronym. It stands for Convective Available Potential Energy. CAPE is one of the most important things meteorologists have to be able to work with to figure out the chances and strength of thunderstorms. We've been doing that for well over a century now. How did they do it when there wasn't a computer to do all of that trapezoid rule stuff for them, or Monte Carlo rule, which would work just fine, or whatever? You are going to love this. You're also going to find it hard to believe that this is true, but this is kind of amazing. What we're going to do is we're going to literally plot this graph on paper. Now, today that almost seems shocking, but of course, 100 years ago, what else were they going to do? There would literally be these charts. These are called skew-T log P diagrams. And they were printed on paper. They were big pieces of paper, too, maybe 2-3 feet in each direction. And some technician would plot the data that came back from the weather balloon. We've been launching weather balloons for that long. I mean, once there was radio technology that we could get the data back from the weather balloon, it was fine. So they would plot all this data onto the graph. And it would be a specific type of paper. Now, it is not 8.5 and 11-inch paper, but I'll work with that because that's the only one you're familiar with. But it was a special paper that was known very well, exactly how big it was and exactly how much it weighed. And from the information as to how big the piece of paper was and how much it weighed, we could figure out 1 gram of the paper takes up how many square inches of the paper. We're making a connection between the mass of the paper and the area of the paper. And it would always be some known amount. Now, when that happens, then we are able to do something amazing. Your friendly neighborhood meteorologist 100 years ago, 50 years ago, before there would have been computers in National Weather Service offices, would literally then sit down with that piece of paper with a pair of scissors and cut that area out. They would literally just go in there and snip, 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 snip along the dotted line and then snip, 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 snip along the red line and literally cut out that area that previously I had shaded in green that I was calling Cape. And then they would take that little scrap of paper that they had just cut out and they would literally weigh it. They had a very precise little scale in the office there. It wasn't a digital scale and it involved moving these little weights back and forth on a little balance beam. It's a little shocking that this existed. And they would literally weigh the piece of paper that they had just cut out. Let's just say for our problem, it's weighed 0.5 grams. Okay. They would, have many more digits than that and so on. I mean, it was a very precise procedure. But here's the deal. If I know the mass of the paper, the little scrap, and I know that this paper has so many square inches per gram, I know how many square inches is my weird little scrap of paper. So that little scrap of paper that they cut out of there, they now know its area. So like in this case, I cranked the numbers and it worked out to that little scrap of paper was 10.39 square inches. But that area is Cape. That area is proportional to the size of the strength of the updraft. And so literally, we would just take that and convert it to the kinetic energy of the updraft. It had units of joules per kilogram. But it would actually, on the piece of paper that they had printed the skew T log P diagram on, it would actually have the information on there, like how to convert from square inches to the strength of the updraft. And it was just proportional. It wasn't a hard calculation. They literally just multiplied it on a slide rule or something like that. This is crazy. So what did they do here? If I had to summarize what we did here, we made a physical model of what we were representing with the integral. In this case, we literally drew it out on a piece of paper and then cut it out with a pair of scissors. Its weight, misspelled here, I didn't realize that, there should be an apostrophe there, which was an easy thing to measure to high accuracy, was proportional to the integral in known ways. And therefore, we got an estimate of the integral without doing any of that terrible math. I'm fascinated by this. I wish I knew more examples of using a physical model if I'd have to think about it or do some Googling to find out more. Okay, so today we've learned about two ways in which we can kind of dodge doing terrible integrals. One involved that Monte Carlo method, which actually lends itself really well to modern computer techniques. Lots of integrals are done that way. A lot of things about how we forecast election outcomes, for example, how they decide that one candidate has 49.2% of the vote and another candidate has 48.1%. It is behind the scenes done by integrals, and the integrals would be too hard to do easily. They're usually done with Monte Carlo methods like that. Because, they hit the button on their computer, and let's say they need 10 million of the darts of the estimates. It's done before they get a sip of their coffee. It's a fast and easy way to make a simulation. Also, we learned about this weird idea of just, sometimes integrals represent something physical. Let's just make a little model of it and use that to figure out the area under the curve. And both of these are good techniques. All right, so I'm going to have a little bit of sort of like an exit ticket for you about this particular lecture, but there's no assignment per se. I don't want you to be trying to compute, or make a program or something like that, unless, of course, that's something you like, in which case I'd be thrilled to see if I can give you a hand with that. All right, thanks for watching, and I'll see you the next time we're together.